quick questions before we begin? Okay, so let me remind you what we're doing. We're looking at a host of phenomenon where we compare and contrast the behavior of conductors and insulators. Conductors have a large store of mobile electrons, not rooted to any particular spot. They will move around as they see fit and are influenced to do so. And then we have insulators, where we have that the electrons are bound to particular nuclei, not free to roam wherever they please. So let me remind you first of all, if you have excess charge on a conductor, since it's free to roam, it'll just redistribute on the surface. That's because that's how it gets as far away from itself as possible, like charge. Whereas on an insulator, if you rub one part of an insulator and take off electrons and put them on that one spot, then that's the spot that ends up being charged. That's on a very practical level. When you guys, you done the electrostatics lab yet? You rub things together? Is that even a lab still?
Sometimes you haven't had our first lab this semester until.
Oh, at all?
Yeah.
Oh, okay. So, well, there's a slab where you rub, like, you know, some fur from some animal of unknown origin. I try not to think about it with like balloons and like things like that. So that's do different things in the triboelectric series. And the main thing to understand is, like, if you're rubbing something like a rubber balloon, if you want it to be evenly charged, you have to rub it evenly. You can't just rub one spot and expect it to take care of itself. So one of the things that makes that lab work better is make sure that you rub something evenly. The last thing you want is for one part to be charged and another one to be neutral, because about this next thing I'm about to talk about, we found that when you place these things in an external electric field, they can become charge polarized. Okay? So when they become charge polarized, one of the things that can happen is that if that field happens to be non-uniform, so this is uniform, but if it happens to be non-uniform, you can literally have a neutral object attract to a charged one. So again, I don't want to dwell on that because I talked about it before, but this is one of the fun things that can happen in this lab, right? So you have a rubber balloon, and let's say you rub it, make it negative. I can't remember, but I think rubber ends up being more negative. And you put it next to another thing that's negatively charged, and you find what they're attracting, what's going on. How can that be? Well, here's why. Is because this is too far away to matter. What you're actually getting is charge polarization of the neutral side. So they're attracting in this way that doesn't make any sense. How can two negative things attract? So it's the attraction of the negative to the neutral side, which is much closer, because if you're neutral, you tend to attract all things that are charged. So in essence, if you don't want to remember that for your lab, just remember, rub your balloon all over, okay? So charge polarization, it can happen if the field is non-uniform. The net effect will be that uncharged objects will be attracted to charged ones. Now, we wouldn't call rubber a conductor, it's an insulator. So, but I'm going to come back to the insulator. I already kind of gave away the punchline last time. Insulators always kind of do sort of what the conductor does, but not as well. So I want to get a few rows down for discussing the conductor, and then we'll catch the insulator up. So here we have a neutral conductor been placed in an external field, which is uniform. We have the charge polarized. We have that the negatives go upstream, the positives go downstream. And the next thing I want to talk about is, well, how much charge polarizes? How does it know when to stop? This is not every single electron on the entire object. If this was every single electron, this would be every single proton, there would be no object anymore, okay? This whole internal thing here is still a mix of protons and electrons. We just don't write plus minus all interspersed, because then we'd have to do it on cover every single object ever with mix of plus and minuses. We only draw the excess charge, right? So there's more of a preponderance of electrons over here. So there's excess minus charge here, and then balanced over here, excess positive charge, because of course the thing is still neutral overall. So when is it that these electrons stop polarizing? It's not all of them. Well, inherently a self-limiting process. Let's take a look at that. So I'm going to do a little play-by-play over here of the interior of the conductor. So here's an electron. Here's the external field. And if the electron has that external field, well, it's definitely going to feel a force upstream. That's what electrons do. They feel a force upstream. Well, then what you have one electron over here and one positive charge left over here. So here's what you have. Let me draw it. So you have one minus that moves over here. So let me label this. This is going to be kind of a time lapse. This is the initial. This is sometime during the process. So what's happened is you have a minus charge that's gone over here. And of course, that left a plus charge over here. We have discussed what the electric field looks like. That's your classic dipole configuration. So it has that shape that we drew last time. But I'm not going to draw it everywhere. I'm going to draw it here in the middle. And in fact, let me not just draw it everywhere. Let me just draw it right here. So E, we call this E induced. The reason why I call it E induced is that this would not exist if it weren't for the external. But it is independent from the external. Okay? So the external field induces the charge to move. You may know from chemistry something about induced dipoles, right? Things that are not dipoles on their own, but they can be induced to be such. So what we have here is an induced field, but of course the external field still remains. And if we were now going to sum those two, what we would find is that E induced is going to take a little snippet away. So the net field looks something like this. So I've tried to draw that arrow shorter than E external. So at this point, E net is smaller than E external. So now we take a look at the next electron. This electron would again feel a force against that net field, but not as strongly. We can think of that in two ways. Well, we can think of it as it's an electron, but in a weaker net field, so it's going to feel a weaker force. Or we can just think of it the common sense way, is that this next electron is not so excited to go over there because another electron already went, right? So it's starting to be less desirable to move to the left. Okay? So this is like the club is starting to get too crowded or something like that. Okay? So maybe you see where I'm going with this. The final state of the system, when the polarization has saturated, is when enough minus charges have gone over here that the field that they make, the induced field, has grown strong enough such that it cancels E external. So now these two cancel, and E net is 0. And so if we took a look at whether a subsequent electron would want to join the party, well, it feels no force anymore. It's too crowded. So that is the self-limiting nature of the process, is when enough electrons polarize, enough electrons move to the left that no more would want to go, because they're as excited as moving up the external field as they are repelled basically by these minus charges that beat them to the punch. Okay? So that is the end of the process. That is when the charge polarization self-limits, when no more electrons would want to go because enough have already gone. Okay? And that's why I call it the final state, because that will be the end of the polarization. Whatever amount of polarization has been achieved is done. So the next line on the chart will be addressing what happens with E net. And specifically, ENet, I will talk about it in two pieces, inside and outside. So, what do we have? Well, inside, we just went through the process, and we find that the net electric field was not only reduced, but reduced all the way down to 0. I guess I'll put it here on the side. So, inside, it's 0. When the system reaches equilibrium, there is no net electric field inside. In fact, let me give you a few details of this process that may not be obvious, may not be apparent from the way I walked you through it. But one of the problems on your homework 1, I can't remember, it's like the 2 copper blocks problem. Has anyone gotten to that yet? Okay. So one of the amazing things about that calculation is that you calculate the amount of charge that is in a normal everyday object you can hold in your hand, and it's ridiculous. It's like 10 to the 8th coulombs. I don't remember the exact answer. Some crazy amount. So if you counted up to all the charge on the electrons and all the charge on the protons, you'd find some ridiculous amount, 10 to the 8th coulombs. 100 million coulombs. Now remember, a typical lightning strike might transfer 3 coulombs. So there's a tremendous amount of charge available in a given object. The only reason why it doesn't seem that tremendous is, of course, you have just as much positive charge and negative charge, so it's basically neutral. One of the goals of that problem that you have is to calculate if you have even slight imbalance in that, like tiny, tiny little percent, it can mean big business, okay? So it can suddenly be very strong. So the only reason we don't notice this is because all the objects we often work with are almost completely neutral, okay? So, as far as what percentage of the charge needs to polarize here, it's the tiny percent. So this is the tiniest percent of the total charge. For any kind of reasonable everyday external field that you might apply to an object, the tiniest percentage of the total charge that's available participates in the polarization, and the rest of the charges, the rest of the electrons, which are mobile, they have no knowledge of this. So this is like the most exclusive club here that you can imagine. This is one that you never even hear about it until after it's closed, okay? So the tiniest little percentage of charge actually goes into the polarization. The vast majority of charge has no idea. You tell them, hey, there's an external field. They say, what external field? I don't feel anything. That's because the external field for them was canceled off by the induced field. So when we say that the net electric field is inside, we gave a name for this. We call it perfect shielding. The vast majority of the mobile electrons within the bulk of the conductor have no idea that there was an external field at all. They are shielded from knowledge of it by this tiniest percentage of charge which needs to polarize to protect the rest from any knowledge of it. And I should also mention that this process is almost instantaneous as well. The reason why it's so quick, by the way, is because in reality, to participate, these tiniest percentage of electrons that participate in the polarization, they don't have to travel across the object as a whole. Here's what really happens. You have an object which is an overlay of positive and negative charge, and when you apply the external field, there's just a slight offset of positive and negative. So it's not like these have really very far to go. They're basically already on the edge. So there's a slight sloshing of the electrons. They basically just take a step over, and there's your charge polarization. Okay. So the analogy that I can try to give you, okay, so let's say you're walking with your kid or your nephew or whatever, small kid, and you're walking downtown San Francisco, okay? So your idea is to perfectly shield them, okay? So you're scanning all the time for any unsavory characters, okay? Trying to do it instantly, okay? And if you see someone over there, then that looks a little bit sketchy, then you say, hey, let's go over here and get an ice cream, right? So the kid has no idea about what just happened, right? So that is the situation that the vast majority of the mobile electrons in the interior are in. They have no idea that the external field is even there because the induced field, which basically pops almost instantaneously into place and uses the tiniest percentage of the total charge, will shield the rest of the mobile charge carriers from this external field. So you can put this to a lot of good use. One of the videos I posted is from the largest Van de Graaff generator in the world. If you don't know what a Van de Graaff generator is, it's basically, we talked about the triboelectric series, where you rub things together like this and get charge transfer. If you attach a motor to it, just so you can get faster rubbing than you could ever get manually, you can transfer a tremendous amount of charge, and then you can deposit it on this big metal dome. So the classic demonstration is someone puts their hand on the dome, some of that excess charge goes up into their hair, and then their hair repels itself, right? So it's all sticking out in different directions. You guys know what this is? Okay. So the Boston Museum of Science has one that's 3 stories tall, and it can cause a lightning bolt of, I think it's over 30 feet, okay? And every day, whatever it is, once in the morning, once in the afternoon, whatever the schedule is, they have some person that works there get into a conducting body. It actually doesn't need to be solid metal whatsoever. It could actually, it's more air than not. It's just a cage. And they have lightning strike that cage with them right inside it. Okay? They even, just for fun, they touch the inside of the cage right where the lightning bolt is hitting. Okay? So why does that work? It works because of this idea of perfect shielding. So as soon as there's a strong electric field in the exterior of the cage, you can have the electrons polarizing, and those will protect the rest. Okay? So for instance, you could have a cavity in here where you can just sit and hang out. Now, of course, the charges in polarizing don't pass through the cavity, but once they're in place, as long as they have a route to go wherever they want to, the field that they make, the induced field, is happy to pass through the cavity. Okay? So another example is, where's the safest place in a lightning storm? It's in your car. It has nothing to do with the rubber tires. If lightning decides to strike your car, it will go right through the tires, melt them, go right in the ground. The reason why it's a good thing is because you're surrounded by a conductor. So basically you have the shielding capability of all these mobile electrons in the chassis of your car, and they will polarize however is necessary to shield everything in the interior, including the electrons in your body, from getting this massive field applied. Okay? So that's perfect shielding. I posted some videos as well of this guy called Dr. Megavolts. Has anyone ever heard of him? Okay, well he takes it one step further, and he wears a cage as a mobile suit. So he has lots of videos of these gigantic lightning bolts hitting him. Okay, you can see his face, it's a metal cage, so you can just see him in there. He's perfectly fine. He'll like jump up in the air, and the lightning bolt will literally hit him in the head and go out his feet, and he's fine. So partial shielding, or perfect shielding, is of some practical use. I guess you may not ever have to do that, but you should know a little bit about there's lots of medical applications where you do not want static buildup. So be aware that, for instance, if you've ever ordered like a computer part in the mail, it always comes in this special bag which is conducting. That just saves it from getting potentially zapped by static electricity while it's in the mail. Okay? So that's perfect shielding. So the next thing we do need to address is, what does the field look like on the outside? The field on the outside, well, this is our classic stretched dipole configuration. The field in the interior might look like this. This is the induced field. That is of course, the field that's canceling the E external. But there's also going to be some field out here. this classic shape looks very similar to a finite parallel plate capacitor. As again I mentioned, these dipole fields are very common, so they'll come to be old friends. It looks like we have a much more difficult task on our hands for the outside. Here we can basically have that right and left are canceled, so the external going to the right and the induced to the left. But this looks like a nightmare on the outside. We're supposed to figure out what's the vector sum. So what's the vector sum of E external, which is to the right, with E induced, which looks maybe like that at that point? Well, if I had to eyeball it, the vector addition maybe looks something like this. That might be E net, just a guess. Let me do another point, I guess. I guess I'll do, I don't know, how about right here? I guess I'll do right here. So there I'd have to do the vector addition of this and this. So E external is easy because it's always to the right, but this E induced field is all this crazy shape. So if I had to guess just by eyeball, I might guess that E net looks something like that. So, am I really supposed to do this for all the entire region? No, there's a shortcut. And let me tell you what the result is. If you notice, there's a common theme, if I've drawn this correctly, that the net field should be perpendicular to the outside surface. That, in fact, is the answer. Outside, it's perpendicular to the surface. Now, of course, I just did 2 points, so that's maybe not sufficient evidence. So I'm going to explain to you why that must be. Why is it that the net field has to meet perpendicularly? The logic of why that is straightforward, or I think most straightforward, if what I do is show you that if it wasn't perpendicular, there'd be something wrong. Okay? So there's a name for that kind of proof. I forget what it is, some Latin name. But the whole idea is, let me pretend it's not perpendicular and show you that that can't be. So let me sketch here. Here is the outside of the conductor. Here's the inside. I'll take one of these electrons in the charge polarization. That's one of many in the charge polarization. And let me put the net field to some random direction and show what's wrong with that. So let me remind you what that net field is due from. The net field is, of course, due to E external and E induced. And if we're interested in how that field might affect this electron, we should technically remember that you can never exert a force on yourself. So when we say E induced here, it's all the other charges in the polarization except this one, right? Okay? So to be technically correct, it's all the charges in the polarization except this one. That's just to be technically correct. Although if you take one little electron out of the entire polarization, it doesn't really substantively change E induced, right? E induced is still pretty much the same as if you took one electron out. So I'm just being technically correct there that you should never apply, ask how a field affects something that is contributing to that field. That doesn't make sense. It's a self-force. So let me take a look. Electrons, which way do they feel a force relative to the net field? Upstream, right? This way. And this force, I notice, can be split into two components relative to the surface. I'll call it F parallel and F perpendicular. So let's discuss these two. So let's imagine that the interior of this room is the interior of the conductor. So here's my electron, and it feels that force, and it gets pulled to the surface. So here it is. And now, if it has a perpendicular force, that's fine, because it can't just jump off the object. We can find out later that if you try hard enough, it will. But for now, that's the end of the line. It's mobile in here, but this is the inside surface. But F parallel, if it had force parallel to the surface, there's nothing stopping it from moving. It can slide around on the inside surface. So what's wrong with that? Well, nothing. But it's still playing musical chairs, so to speak. We're still in the during phase. We're still in the during phase of everything getting settled. When we get to the end, by definition, that's when everything has settled down. The polarization is what it is. And so